Okay, so we're going to start with inverse functions, which is the first of the two concepts that we're going to be studying today. So I'm going to refer back to that number machine that we had in grade 9 that we use a lot. And remember that again, I said that a function is always comprised of three elements. You have an input, you have a rule, you have an output. The process of going from the input to the output is what defines the function. Okay, and last week we actually touched on different types of functions. We touched on one-to-one functions, we touched on many-to-one functions, and we touched on one-to-many, which are not functions. Remember that, using the vertical line test. We're going to come a little later to that. Okay, so going from the input to the output defines the function. Going from the output back to the input will define the inverse of a function. And this is, so here I've got an example of an all grade 9 number machine where we had an input, we had the rule 3x plus 5, and we had the output. So we go from 3 through here. 3 times 3 plus 5 is 14. 0 times 3 plus 5 is 5. Minus 1 times 3 plus 5 is 2. And that's just your standard function. Now, the moment we reverse that order and we start going from the output back to the input, we have to follow, for us to be able to follow to find the input, we will have to follow the output using the reversed operations in the reverse order. What does that mean? It means, how did I get from the input to the output? I put a number in here, first multiplied it by 3, and then added 5. Whereas if I'm going to go from the output back to the input, I'm going to start and go backwards. So I'm going to say, the last thing I did was add 5. So going from the output back to the input, the first thing that I'm going to do is subtract 5. The first thing I did was multiply by 3. So the last thing that I'm going to do going back to my input is multiply by 3. So if I start from 8 and I go 8 minus 5, that is 3. And 3 divided by 3 is 1. And I'm allowed to then get to your input. So if I had to substitute 1 in here, I will get back to the output. So that means that my process is now reversed and is correct. From minus 1 the same. So if I went minus 1 minus 5, that would be minus 6 divided by 3 is minus 2. If I were to put minus 2 into the function, I will end up with minus 1. So what I'm doing by going backwards is actually generating what I call the inverse of the function. So the inverse of a function is nothing else but reversing the process, going from the output to the input. In the inverse function, the output becomes the input, okay? And the input becomes the output. So it's basically the original function turned upside down. Okay, now I can actually define my rule for the inverse function then as x minus 5 over 3. Okay, now the next part, which is the notation, and this is very, very important. Okay, how do we notate the inverse of a function? The notation for the inverse of a function is always used as f to the power of minus 1. And I just want to spend a little time explaining about this power of minus 1. This power of minus 1, and you will see it in the pre-recorded video, has nothing to do with the laws of exponents. In grade 9, when you study laws of exponents, you learn that a to the power of minus k is equals to 1 over a to the power of k. So whenever you had a minus 1, so if you had x to the power of minus 1, that wrote as 1 over x. In the case of function, that has nothing to do with 1 over. Okay, so this is a complete different concept. When you see f to the minus 1, is actually referring to the reverse rule, not referring to the reciprocal, which is the actual name of this. It doesn't refer to the reciprocal of a function. Capish? Okay, right. Now let's go and show you how can we find what is the algebraic algorithm for us to find the inverse of a function. Okay, so to find the inverse of a function, and I'm going to use exactly the same function that I was working here. We already saw what the inverse was by using the rule and following the rule backwards. Okay, what I'm going to do now is I'm going to show you how can we or what are the logical steps that we follow to arrive to that inverse of the function. Okay, so here is the same function. I don't want to alter it for now. Okay, we have the function 3x plus 5. The first thing that I recommend you do is, if your function is given in the form f of x equals to something in terms of x, that you swap that f of x to y. Remember that your f of x is your y, or the value of y in your function. And once you've done that, what I want you to do, and here is a very important step, is you
Sorry,
have to,
sir.
yeah?
Could you please zoom out just a little bit?
Pardon?
Could you please zoom out
Zoom
just a
out.
little bit? Yes,
Certainly.
please.
Okay. Enough?
Thank you, sir.
Okay. Okay, so again, here is a very important step, and that is, if you look from this step to the next step, all we've done is we swap the x and the y. So the x and the y have been swapped around. And this is very, very important, because this is the key to me being able to determine the inverse of a function. Okay? Once I have swapped the x and the y, my next step will be to solve for y. Okay, and this is just like a normal equation, so I will take the 5 across to the other side, 3y equals x minus 5, and then divide by 3. So I could write it like that, or I could just use the 3 as my common denominator and write it as 2 split fractions in this way. Makes no difference either way. And then the last step I should then do is now reconvert. Remember that my function was given in the form f of x equals 3x plus 5. I should now be able to express my function in the form f minus 1, which means the inverse of the function f is equals to x minus 5 over 3. Okay, any questions so far? All cool? I take it. All right, so let's now go to talk about domain and range of a inverse function. Okay, so I'm going to start with perhaps the simplest, but in some cases the most profound of these functions to explain what I want to explain when it comes to domain and range to you. So here we have the quadratic function, the nice parabola as we call it before. All right, here is the graph of the parabola. Okay, so the domain of the function, remember, domain refers to what? Refers to all the values of x that are possible, that I can possibly use in this expression. Since there is no square root and there is no fractions with the x in it, I can say that the domain of this function is all the real numbers. Okay? In the case of the range, it doesn't matter whether I enter a negative, I enter a positive, or I enter a 0, I will always get values that are 0 or positive. And thus, my range in this case will be all the values of y which are 0 or positive. So from 0 to infinity, those are all the possible solutions that I'm going to get. Okay? Right. So there is my function. I'm going to draw a line here. Now let's focus on the inverse of this function. When I look at the inverse of the function, and I've just calculated the inverse, you can actually follow the process as I did before, so that you can get to this point. Okay? And that's how you're going to arrive to the inverse. So it's plus minus the square root of x. I've just taken the liberty to draw the graph of this function. So the part in pink is the plus square root of x. The part in green is the minus square root of x. So as you can see, it looks almost like a split function. So it's got two pieces to it. Okay. Or, and this is where the controversy comes, this graph is not a function. Remember last week when we talked about function, we say a graph represents a function only if it passes the vertical line test, which the graph of x squared does pass because it only touches the graph only once. But when I come here, and if I just draw a line right there for interest sake, I've got 2 points of contact. I've got a point of contact here. I've got another point of contact there. So in this case, I've got a one to many. And remember what we said last week, one to many is not a function. Okay, so this is not a function. The original is a function, but the inverse is not a function. And some cases you're going to find that. You're going to find that the parabola, the inverse of the parabola is not a function. The inverse of trigonometric functions, most of them are not functions as well. So how can we achieve this quadratic function or the inverse of this quadratic function to have an inverse that it is a function? We have to restrict the domain of the function. So we need to restrict the domain of the original function. What does that mean? It means that instead of me saying I want to find the inverse of the whole function x squared, I would say I want to find the inverse of a function x squared only for the positive values of x, which will give me this pink function, the one at the top. Okay? Whereas if I wanted to find the inverse of my function for the negative values of x, okay, for the negative values of x, that will give me the green function. So it will be this graph over here. So by me restricting the domain of the function, I can guarantee that the inverse is also a function. Okay, now as far as domain and range goes, remember what we did in order to find the inverse of a function. We swapped the x and the y. We swapped the x and the y. Okay, the x in a function, as you know very well, the x represents what? It represents the domain, and the y represents the range. Since we swap the x and the y to find the inverse of a function, in the case of the domain and range, the domain and the range of the inverse is always the opposite of what it was in the original function. So the domain of the original function becomes the range of the inverse and vice versa. The range of the original function becomes the domain of the inverse. Is that clear? Okay, I will take that as a yes. Right. This is as simple as domain and range or inverse functions come about. Okay, so inverse functions, all I need to know about inverse function is the following. I need to know, first of all, how to determine the inverse of a function using algebra. So if I was to find the inverse of this function, determine an inverse of each of the following functions and state whether the inverse of this function is a function or not. Okay, here is my first example. This one is on your textbook. The worksheet is on Google Classroom. Okay, so I'm going to find the inverse of this function. First thing that I'm going to do, since I already got it written in the form y in terms of x, I'm going to start by swapping the x and the y. So this will become x equals to y squared minus 64. And I'm now going to solve for y. So I'm going to take the 64 across. So this is x plus 64 equals to y squared. Okay, and now remember to solve for y, which is what I'm going to do here. Okay, I will have to say this is plus and minus the square root of x plus 64. Okay, and that is then my inverse function. My inverse function, y to the minus 1, I'm going to call it so that I can differentiate it from the original function, is the function plus minus square root of 64. Okay, now the question here is this. Is this a function, yes or no? Okay, this one is not a function. Why? For a single value of x, let's say you take the value of x of 17. Okay, for x equals 17, right? 17 plus 64 is equals to 81. Okay, and 81, the square root of 81 is 9, and I'm going to have two values of y, plus 9 and minus 9. And that's what we mean by the inverse not being a function. Because for a single value of x, for 17, for one x, we had two possible y's. So this is a case of a one-to-many relation. And remember what we said last week, a one-to-many relation is not a function. Okay, so that is one of the examples. So I would say, in this case, f of x equals x squared plus minus 64 is a function, but y minus 1, which is equals to plus minus the square root of x plus 64, is not a function. Okay, and like that, you will do the next two examples. And that is as far as the inverse of a function is concerned. The three skills that you need to know when it comes to inverse of a function, and I'm going to write them here for you, is number one, you will need to be able to determine inverse by using algebraic methods. Number two, you should be able to state domain and range of both the function and the inverse of the function. And those are the two skills that I want you from here. So whenever we talk about that inverse of a function, you'll be able to write it in that form. You'll be able to get the x and the y, swap them around, solve for y, and that will give you the inverse of a function. And remember, when it comes to the domain and the range, you will achieve that also by turning the function or swapping the domain or range of the original function to get your range and domain for the inverse function. Okay. Any questions when it comes to inverses? All happy with that? Right, I'll take that as a yes. Right, the second part of our lesson today is to talk about split functions. Okay? Can you all see the diagram that I've got on the projector? Everyone?
Yes, sir.
Yes,
Thank
sir.
you.
Yes,
Thank
sir.
you.
Yes, sir.
Thank you. All right. So here is an example of a split function, and I'm sure that you've seen a split function before. You've seen another example of split functions before. Okay. We did the function, remember, f of x equals to the absolute value of x, which was a split function. If you remember correctly, it's written in two ways. So it's x if the x is bigger than or equals to 0, and it is minus x if x was less than 0. And that's how we define the absolute value function. So here is another case of a split function. What is a split function? And again, and I'm going to explain it like I did in the pre-recorded lesson. In mathematics, so far, you've been given these pretty functions, so to speak. And when I say pretty functions, I'm just simply referring to your quadratic function, your hyperbola, your exponential function, which are all very nice, smooth functions that can be drawn. But life is not like that, unfortunately. Okay? When you analyze the production of a factory, for example, and you try to model that mathematically, that model is not a nice parabola or a nice hyperbola or a nice exponential function. We wish it was like that. Unfortunately, it isn't. Okay, and that's where split functions actually become very useful, because split functions actually analyze certain behaviors of functions in particular intervals. And this is what is so remarkable about split functions. So what are the elements of a split function? You have two elements. The one element is the equations, and those equations are the ones that are going to define how my split function is defined. And then you have your restrictions to the domain of the function. What this basically means is that if the function, the value of x, so to the values that are bigger than 0, to the right of the y-axis, my function have the form x plus 3, which is a straight line. Okay? However, from the origin, from 0 to the left of the y-axis, my function has the form of 2x minus 1, which is also a straight line, but it's a straight line that looks slightly different. I'm going to give you some examples of split functions a little later. I just want you to understand how a split function works. So let's take this example now, and I say I wanted you to find the value of f of 3. Okay, when I look at the value of x here, which is 3, the first thing that I need to do is I need to analyze and say, where am I going to substitute? Is it in the top function or in the bottom function? I need to then compare 3 to my restrictions. So 3 being a value bigger than 0 means that f of 3 will be a value that I will obtain by substituting in the top function. So f of 3 is going to be equals to 3 plus 3, which is equals to 6. However, if I wanted to determine f of minus 2, for example, I will then have to say, how will I obtain f of minus 2? Let me find out what the value of x, or where is minus 2 in relation to x in these two restrictions. Minus 2 is a value that is less or equal than 0. So it's a value less than 0. That means that f of minus 2 will be evaluated in the bottom half of my equation. So in this case, to calculate f of minus 2, I will say 2 times minus 2 minus 1, sorry, not plus 1, minus 1, and that will be equals to negative 5. So f of minus 2 is minus 5, whereas f of 3 is equals to 6. So it is very important for me to always analyze or to check carefully where is it that I need to evaluate my function when it comes to a split graph. Okay? Right, so here is another split graph. Now we have, this split graph is defined as x, the value of x, for all the values of x that are less or equal than 1, and is defined as 3x minus 1 for all the values of x which are bigger than 1. So if I was to calculate g of 5, for example, where am I going to evaluate g of 5? Where is 5 in my restriction? 5 falls under the values that are bigger than 1. So g of 5 will then be evaluated in here. So I will say g of 5 is equals to 3 times 5 minus 1, which is equals to 14. Okay? If I needed to calculate g of 3, where am I going to evaluate it? Still in the bottom one, because 3 is still bigger than 1. So it will be 3 times 3 minus 1, which is equals to 8. But if I had to evaluate g of, say, minus 2, where am I going to evaluate it? I'm going to evaluate it at the top, because minus 2 is a value which is less than 1. And in that case, the value is exactly the same, so it stays at minus 2. So g of minus 2 is equals to minus 2. Where would I put g of 1? Where would I put g of 1? Anybody?
In the top, sir.
You put it in the top, because the values, the equation in the top is the one that includes the 1 as one of my solutions. Okay, so g of 1 is going to be equals to 1. Okay, any questions? All clear? I assume yes. Right, so here is another example. Now I've done it, the calculations already, so that I don't waste time with that. And again, here we have a split function that where my domain is separated around the value of 2, or minus 2 in this case. So for any value of x which is less than minus 2, my function is going to be defined as x squared plus 2x plus 1. And for any value of x which is bigger than negative 2, my function is going to be defined as 1 plus x squared. In that case, if I need to calculate g of minus 5, because minus 5 is less than minus 2, I will substitute it in the top equation. And that case will get 16 as a value. If I had to calculate g of minus 2, because minus 2 is still included in my top domain, then I will also substitute it in the top equation. Whereas if I needed to find g of 1, because 1 is a value that is bigger than minus 2, I will then be able to substitute it in the bottom part of my equation to be able to find the value of g of 1. Okay? Right.
Sir, Jared typed a question out.
Okay, I wasn't looking at that. Let me have a look. Would it be possible to have a value which can be used in both equations in a split function? No, because most of the time the split functions will be split along a particular value of x. So let's say in this case it's minus 2. A value is either bigger than minus 2 or less or equal than minus 2. what can happen, Jared, is that you may have a question, or you may have a function that has a value that doesn't exist. So what I try to say here is that you could have this, you could not have that equal there. So let's say if we didn't have that equal there, how would that change my equation? Well, the way in which that would change my equation is that if I didn't have that equals to 2 there, then these cannot be calculated, because the value of x equals to 2 does not belong at the top or at the bottom. Okay, but you will always find that the values that you need to substitute are always values that are only in one part of the domain or another, but not in two parts of the domain. Does that answer your question? Okay, right. Okay, so let's go. Now, let's talk about this function. This specific type of function is called a step function. Okay. Some mathematicians call it funnily the ladder function, because it looks almost like a step ladder. You're walking in steps up and down. Okay. And this is a function where if you look at the equations, none of the equations actually contain the x. So there's no variables in the equation, which makes this one of these graphs, it makes them actually horizontal, it makes them flat. Now, what is interesting about this equation is, if you look carefully, look at how my intervals have been defined in my equation, and look at the look of my graph. So I'm just going to start from the first part, which is between 0 and 1, the function has a value of 0. Okay, as you look here, it starts with, and I'm going to use a red so that I don't get confused with it. So it starts with the dot at 0, because 0 is included in my domain. Then it does a little line until it gets to 1, and then when it gets to 1, it makes a open circle. That it means that you will get very close to 1, but you will not have a value. At 1, it does not have a value here. Okay, what is the value at 1? The value at 1 actually jumps to here. Again, check out, there's a dot here because x equals to 1 for this part, and then a little line, and then a circle again because it's not including the 2. And then it jumps again from here to that side there. So you have a little dot here because the 2 is included in the next one, and then a line, and then a circle again. Okay, and that is a step function. Very careful when it comes to the points and the dots, because the points and the dots actually tell me which part of the interval am I including and which part of the interval I am not including. Okay, any questions there? Okay, domain and range of a split function. Okay, I'm going to start with the domain. Okay, the domain is the set of all the input numbers. Again, just exactly the same way in which we did with the previous function. Any value that you can put into x will be your domain. Okay? Remember, what you see on the right-hand side, okay, and I'm going to make that very clear, do not confuse that with the domain. This is not the domain. These are the restrictions to my domain. My domain in this case starts from 0 to 3. That's my domain because it starts at 0, it ends at 3, there is nothing on the outside. So this is going to be the domain of the function. But each one of these 3 little intervals here are not the domain. They are the restrictions to the domain under which these equations are ruled. Okay? So be very careful when it comes to stating restrictions to the domain and stating the domain. The domain stays as is normal in the function. All the possible values of x that the function can take will conform my domain, and obviously all the set of outputs will conform my range. Okay, so there is nothing really new when it comes to domain and range in split functions. Right? Now I'm going to talk about something very important, that is points of discontinuity. Okay, let me just put it down here so you can see it. There we go. Points of discontinuity. Okay? What are points of discontinuity? As you can see, these split functions are not always continuous functions. Sometimes they jump, and this is the case of the function that I've got here. So I'm going to start with this function, which is defined, you've seen this function before, okay, as x for any value of x that is less than 1. So that means that before 1, from 1 to the left, the function is defined as y equals to x, okay? And in this case over here, I'm going to draw a dot, because remember that x can be 1, okay? Whereas after 1, from all the values of x that are bigger than 1, my function is going to be defined in this way. So all I need to complete this function here is I'm going to have to draw an open circle over here, because remember that at 1, that function doesn't exist, okay? The function that exists at 1 is the one below. So this area here, this gap over here, is what tells me that my function has a jump. And later on, we're going to actually refer to that as a jump discontinuity, okay? So the function is not completely continuous, it's not smooth. You cannot draw it without lifting your pen. So if you're going to draw this function, you have to draw it up to here, then lift your pen, go here, and continue drawing the function. And that's basically the practical way of looking at a discontinuity, okay? The same thing with the next function, which is your step function. If I look at my step function here, okay, you have that this function is also a function that contains jump discontinuity. So you go from this point to here, and then you jump to get to the next one, and then you jump to get to the next one. Okay, so this is what we call a jump discontinuity. Now, these holes also have certain connotation, and we're going to touch that in a moment when it comes to functions. Understood what we mean by discontinuity? A discontinuity is a point or is an area of the graph where you actually have to lift your pen to be able to continue drawing your graph. Okay, so you cannot just draw the graph with only one trace. You have to lift your pen and continue tracing elsewhere, and that's basically how you look at discontinuity. All right, so axis of symmetry. And again, this we've already touched when it comes to the graphs of functions. So axis of symmetry, remember, sorry about this vertical line here, it was meant to be passing through here. This is my axis of symmetry. Obviously from the printing it went haywire. So my axis of symmetry is this red line. And basically what this axis of symmetry tell me is that my function is symmetrical along that line. So if I was going to reflect the one branch of my function onto that line, I will get the other branch of my function. Okay, and this in this case applies to the absolute value function. It also applies to the quadratic function. The parabola also has an axis of symmetry. The hyperbola also has an axis of symmetry, and you would have studied that in core mathematics. Okay, I'm not going to spend time on the axis of symmetry because that's not relevant to what we want to do. We want to focus on split functions. Okay, again, this is also for your information. When we talk about maxima and minima for a function, which is also what we call the extreme or the extremum of the function, okay? A minimum value is the lowest value that the function can ever achieve. This absolute value function has a minimum value of 1, okay? And it doesn't have a maximum value because this function continues indefinitely to the left and to the right, so it only has a minimum value, okay? This function over here also has a minimum value at -2 because it's the lowest point that the function will ever achieve. It doesn't have a maximum value because you will say, well, look at that, it's flat there, so my maximum could be 2. But if I look on this side of my function, that function is continuing, so there is no maximum value, there is a minimum value. There might be functions that have a maximum but not a minimum, and that is the case, for example, of your parabola when it's upside down. This function has a maximum, not a minimum, okay, because it continues indefinitely towards -infinity, but it reaches the maximum value of, let's say, 5 for this case. You may have functions that have a maximum and a minimum, and you have functions that may not have maximum or minimum, okay? Again, this is all part of information, right? Let's talk about increasing and decreasing. How does a function increase and decrease? Okay, So let's take an example of this function over here, which is one of the ones that I showed you in the previous slide. Okay, how this function increases and decreases. Okay, we have now, how do I analyze whether the function increases or decreases? I will use my vertical line test again. Okay, when I swipe a ruler from minus infinity towards infinity, I can analyze what the function is doing. So if I look at this function now, and I'm swiping my ruler from minus infinity, what is the function doing here? The function is going down. So in the interval from minus infinity to -2, which will be the value that is here, my function is decreasing, is going down. Okay? From -2, now from -2 to +1, which is this bottom section of the function, my function is now increasing. As I'm moving the ruler, you see the function is going upwards. So in the interval between -2 and 1, my function is increasing, it's going up. Whereas after 1, from 1 to the right, my function is constant because it's a horizontal line. Okay, so for what intervals is this function increasing? I will say the function is increasing, okay, for, and I'm going to start here, I'm going to say, let's go down here, function is increasing for the values of x, which are between -2, and then please note that I've put an equals -2 because there is a dot here, so that function is increasing from here, including the -2, all the way to less or equal than 1, because it's also including here. Where is the function decreasing? I will write it in interval notation as x element of the interval from minus infinity to -2, and I'm also going to leave it open because I have a circle over here. Okay, another way I could have written that, I could have said x is less than -2, and that's another way of saying that it is decreasing for all the values of x that are less than -2. And constant, which is the flat side, the horizontal line, okay, in this case it is constant for all the values of x which are bigger than 1. Okay, so that is again how we analyze the increment of the function, whether the function increases or decreases in a particular interval. All right? Okay, so in terms of theory, this is all we need to know about inverse functions and also about split functions. Any questions? No questions. Okay. Right. Let's go now. I will give you a little bit of time to go and grab your textbooks. We're going to look at a couple of examples of split functions looking through your textbook. Okay. So I want you to open your textbook on page 67. Textbook page 67. Okay. In the textbook on page 67, you have a split graph, and please note that split graph now is not the same easy split graph that you had with only 2 functions. Now you have 3 pieces to that graph. Okay? Now, the sketch of the graph is on the screen, as you see now. And what I want you to check with me, or what I want you to analyze with me, is the questions that they've asked in the book. Okay? The first question that they ask you is determine the values of f of -2 and show on the graph with the letter A where you will find this answer. Okay? So f of -2, okay, remember, where am I going to evaluate f of -2? I'm going to evaluate it in the top side. Why? Because the top side applies to any value that is less than -1. And that is this part of my graph. It's this area here, the section here, which is the function x plus 3. Okay? So what is the value of f of minus 2? I have to substitute it in the top side, and that value is 1, and that is the value that I've got here, which is marked with the letter A on my graph. Okay, part B says determine or find f of 1. Okay, f of 1, again, when I look where 1 falls into my function, it falls in the second restriction to the interval, because 1 is a value between -1 and +2. 1 is a value here. So when I substitute it, that second part is constant, so it doesn't matter what value you put in the x, your answer is always going to be 2, and that is this point here. So f of 1 is equal to 2. All right, the next question, and this is very interesting now. Okay, what is the value of f of -1? F of -1. When I look in my equation, or when I look in my function, okay, f of -1, this part of the domain is restricted to the values that are strictly less than -1. The second interval is restricted to the values that are strictly bigger than -1, and they could be equal or less than +2. But 1 is nowhere included here. So when I need to substitute -1, when I need to substitute -1, I've got no place to substitute -1. So what am I going to do in this case? I'm going to say, well, f of -1 does not exist simply because I don't know where to place -1 here. -1 doesn't belong in that interval. It doesn't belong in that interval. It definitely does not belong in that interval. And that's why I say that f of -1 does not exist. Clear? Okay, the next question is determine f of 2, and again I'm going to look at now where is f of 2. Is not at the bottom, because the bottom is only defined for the values that are bigger, strictly bigger than 2. Okay, it is in the middle, because here I've got included when x is equal to 2. So f of 2 is going to be equal to 2. Okay, the next one is f of 4, and find that in the graph where you will mark it with the letter B. So f of 4 in this case, when I look at 4 again falls under this section here, because 4 is bigger than 2. So I'm just going to substitute 4 in here and say -1/2 times 4, which is equals to -2. So f of -4 is equals to -2. Okay, now comes the interesting questions here. Question F says, what are the zeros of the function? And please, I want you to highlight this as a very important, okay? The zero of a function, and maybe you would have done that in core mathematics, the zero of a function is basically the values of x that make the function 0, okay? A practical word for the zeros of a function is the x-intercept of the function. So whenever you see the word 0 of a function, the 0 of a function is your x-intercept of a function. Okay, so keep that in mind. All right, now we're going to the next two parts, which I want you to look at very, very careful. The first one, question G, says, when x gets very, very close to -1, what does the function get very close to? Okay, here is -1. Okay, and what this is referring to is, as my value of x approaches -1, as I'm getting to -1, okay, my function is approaching that value there. It's approaching 2. Okay, if I was to approach -1 from the right, because some of you may say, no, but why are you doing it from that side? Why not from this side? Okay, you can also do it from that side. And if you're doing it from that side, as you approach x from that side, your function is also approaching this value. Okay, but remember what we said at -1. My function at -1 does not exist. Okay, so what do we talk about when we mention approach? Well, that is what we're going to define in our next lesson as limit. This is what we're going to define as limit. What happens as we approach a value from both sides? So if I approach x from the left, my function approaches 2. If I approach x from the right, my function also approaches 2. So even though this is part of the next lesson, I could say what this means is basically that the function at -1 doesn't exist, but the function does have a limit, because as x approaches -1 from the left and from the right, my function approaches a same value, and that value is 2. Okay, so we could say, and again, this is just a preamble for next lesson, is we could say the limit at x equals -1 is 2. The function does not exist, but it does have a limit. So very important to be able to gather these questions, because this is what is going to make it clear for us when it comes to limits. The last question H of question exercise, or question 1 exercise 3.4, what happens to the function f of x when x gets very, very close to 2? Now we're talking about this function here, and this is the interesting part, because if I approach 2, 2 is here. If I approach 2 from the left, my function is at the top here. My graph is at the top here. So as I approach 2, the function also approaches the value of 2. If I approach it from the left. However, if I approach 2 from the right, and remember that I am approaching the value of 2, if I approach 2 from the right, my function actually is getting closer and closer to what? Closer to this value, which is -1. Okay, so in the first case, in the case of question G, when the x approached -1 from both sides, we went to the same value. Now here we have a different case. As I'm approaching 2, if I approach 2 from the left, my function has a value of 2, which is very different than if I approach 2 from the right, because if I approach 2 from the right, I'm looking at this side of my equation. Okay, and that's where we're going to get into in the next lesson when it comes to limits. Clear? Any questions so far? This will be perhaps the most difficult part of our lesson today. Have you any questions? No questions? Right, so here's question number 2 of that same exercise. Okay, now question number 2 has quite a few split functions. Okay, so if you look at that graph, that actually has 5 different equations. So I'm going to take you through those equations one by one so that you can see the different steps in this function. Okay, starting from the left-hand side. So for any value that is on the left of -2, the function has the form 3x plus 9, which is this straight line. For any value or at -2, when x is equals to -2, the function then has a value of 5. Between -2 and -1, which is the next step, the function has a constant value of 3. From -1 to +2, the function has the form of -2x squared plus 5, which is this little piece of a quadratic function. And finally, for any value of x that is bigger than 2, the function has the form of the straight line x minus 2. So here is my split graph of this function. Now we're going to answer the questions that they're asking. What are the zeros of the function? Okay, where is this function touching the x-axis? This function has 2 zeros. It has a 0 on this side here. Okay, so I'm going to calculate that by making the top side, because that's the portion of the graph where I have the first 0, making that equals to 0 and solving for x. And that's going to give me, if I made 3x, let's put it down a little bit, 3x plus 9 equals to 0, and I try to solve that, that would give me 3x equals -9, and x equals -3. So 1 0 of this function is x equals -3. The other 0 happens in this portion here, because as you can see, this quadratic function, this parabola, does touch the x-axis. So my second 0 will be calculated by making -2x squared plus 5 equals to 0 and solving for x. So that's going to give me that -2x squared is equals to -5. which means that x squared is equals to 5 over 2, and x squared is equals to plus or minus the square root of 5 over 2. However, the negative side of the square root of 5 over 2 does not apply here because I'm only looking at this portion of the graph, the portion between minus 1 and 2. So this value here, and I don't want to calculate it now, is the square root of 5 over 2, and that's the second zero of the function. So therefore, x is equals to the square root of 5 over 2. And those are the two zeros of the function. The next question is, show with the letter A where you will need to read the of f of negative 1. So f of negative 1 is over here. Where am I going to read it off? I'm going to read it off over here. Okay? F of negative 1 will be read on this side. And what is the value of f of negative 1? It does not exist. F of negative 1 does not exist. Okay? Right. What is the value of? That's the next question. What is the value of f of negative 2? So f of negative 2, is it that value or is it the top value? Remember, that means it's not a value. The dot means that it's a value. So f of negative 2 is equals to 5. Okay? The next one is f of negative 1. F of negative 1, we just quoted it now. F of negative 1 does not exist. And I'm going to start using the term DNE because we're going to be using that for a little while now. The next one is f of 0. F of 0, what is the y-intercept of the quadratic function? F of 0 is equals to 5. Okay? And the last one is f of 2. Again, for 2 here, we would have had two possible values. That one means that is not included. That means that is included. So f of 2 has a value of negative 3. Okay? The next question here says, when x gets very close to negative 2, what values does the function get very close to? And again, this is trying to explore limit by looking at proximity. So the question here is basically asking, what happens to the function as I approach negative 2? Now, there's two ways of approaching negative 2. You can approach it from the left, and you can approach it from the right. Okay? As you approach negative 2 from the left, your function is approaching the value of 3. 3 is here. Okay? As you approach negative 2 from the right, your function is also approaching the value of 3. So my answer to that question, question D, will be when x gets close to negative 2, the function gets very close to 3. So I would say for part D, okay, f of x gets close to 3. Okay? Next question says, when x gets close to negative 1, what values does f of x get, to negative 1, what values does f get close to? So again, now I'm approaching negative 1, so I'm going to use a different color here. Negative 1 is on this side here. Here's negative 1. So as x approaches negative 1 from the left, and x approaches negative 1 from the right, what value does the function approach? So as x approaches negative 1, my function approaches 3. As the x approaches negative 1 now from the right, my function is also approaching 3. Okay, so again, I can say that for the negative 1, f of x, so that's part E, f of x also gets close to 3. Okay? And the last part that says when x gets close to 2, what happens to the function? Again, I'm going to look at now what happens in the vicinity of 2. So what happens when I approach 2 from the left? As I approach 2 from the left, my function tends to have a value of negative 3. As I approach 2 from the right, so if I come from this side, the function tends to have a value of 0. Okay? So what happens in this here, so that as I approach 2 from the left and from the right, the function, so this is part F, my function jumps. Okay? And these, or all of these cases, is what we call discontinuity, which is something that we're going to study when we do limits in our next lesson. Okay, any questions? Any questions? Right, so if there is no questions, that is our lesson for today. I'm going to stop the recording now. This is our lesson for today. So today, just as a matter of summary, we've learned how to look at the inverse of a function, how to determine the inverse of a function by using algebra. And also we've looked at split functions, and we've looked at what happens to the behavior of split functions. Okay? Have you any questions, guys?
Not really, sir.
No, thanks, sir.
No, sir.
No,
Thank
sir.
you, sir.
Simple enough. Okay, for the pre-recorded lesson, you can go to Google Classroom. I'm going to put this lesson once it becomes available. I'm also going to upload it to Classroom so that you also have this lesson. They are slightly different, but the line of the lesson is exactly the same for both cases.
Thank you, sir.
Okay,
Thank you,
Thank
sir.
you, sir.
guys, just do the worksheets. Again, I will be available just before the lesson next week. If you have any questions, we can actually do that. So I will log in at 2:30. If you have any questions next week, join me. Otherwise, we have our lesson at 2:30 as normal. Okay.
Thank you,
Yes, sir. Thank you.
Cheers,
Yes,
guys.
sir.
Have a
Thank
good
you, sir.
afternoon.
Enjoy,
Have
sir.
a nice weekend.
You
Thank
too,
you,
sir.
You too, sir.
Bye.
Thank you, sir.
Thank you,
Ciao.
sir.
Bye.
Bye.
Bye. Thank you, sir.
Bye.